very much. It's good to be here, and actually, maybe the end of my talk, if I ever get there, is going to be similar, or is going to create the same kind of issues, perhaps, as what Bernd showed. And but in the meantime, I simply wanted to talk a bit about the single layer iron selenide on STO. That's what we thought we were going to talk about initially, but I think the program has changed a little bit, but that doesn't really matter. So the single layer FeSe is, iron selenide itself, of course, is also a superconductor. It doesn't have a magnetic transition. So we all feel that, hey, this is a nice thing to study. Transition temperature of bulk iron selenide is very low, about 8 degrees Kelvin, if I remember correctly. And it has a very, very low carrier density, a very low Fermi energy, and it has only a Fermi pockets, only electron pockets, and apparently no hole pockets in it in the single layer type material. Okay, and that all creates interesting questions again about magnetism, about the interaction of magnetism and the lattice, which is extremely strong, as we know already from Ole Gunnarsson's or Ole Anderson's work from way back when, just from density functional. And I'm going to show a little bit of that kind of stuff. So these are the people that were involved in this. Fengmiao Li done quite a bit of density functional theory together with Ilya Elfimov. Ke, you know, is a new professor at UBC, and he has done very nice work on single layer FeSe on STO. Chung Liu, who has done some angular resolved photo emission also together with Ryan Day. Okay, so I'd like to talk a little bit about the replica bands and RPES and electron-phonon interactions, then a bit about the atomic and electronic structure issues. Local iron fluctuating magnetic moments is another thing I want to talk about. And it'll be a different kind of fluctuation than we generally think of it as, for example, in the case of the cuprates, and charge transfer from the STO substrate to iron selenide. And I think I won't have time for the double layer iron selenide type work. Anyway, well, I should mention the double layer because this is one of the big problems, of course. You know, we all have problems with what actually the structure is, what actually the chemical composition is. Even in the case of iron selenide, one claims that from Kava's work, that the line phase, the real line phase is something like 1.01 iron selenium. Okay, so there's extra iron in there of a very typical, very small amount, which gets me to think about, you know, your very low concentrations of manganese, for example, that really affect the superconductivity and the behavior of your 111 crystals, which you, of course, have very nice crystals. The iron selenide on STO as a thin film or as a monolayer, of course, is even much more difficult. We actually don't know really, as far as I'm concerned, what the chemical composition is. We also don't really know what the structure is. But we know something about the electronic properties. And if you put iron selenide on STO and dope it with electrons, right, you get a transition temperature up to 65 Kelvin, at least from spectroscopy, and that's from tunneling or from photo emission, actually looking at the superconducting gap and so on. From transport, it's more like 40 Kelvin that you get. Okay, let me take this out of the way here. So you all know what the structure of iron selenide is. It's not polar, which is very nice because many of the other materials, as you know, are polar, and that always creates a bit of a problem for surfaces. So for photo emission, it's very, very nice to have a non-polar material. Now, of course, when you put it on strontium titanate, it may be polar. As a matter of fact, it probably is. But let's just go ahead with this first. So the photo emission results, this is from Lee, Nature paper, ZX Shen's group in Stanford. And you see that there, you see at the gamma point, the left hand side here, I think oh, you can't see my cursor now.
We can see your cursor, yes.
Yeah, you can see it? Okay.
Yeah, we can see it.
We see your pointer.
Yeah, okay. So on the left-hand side, you see that there's a big gap. There's no whole pocket. It's far away from the Fermi energy. And in the middle there, you see the dispersion at around the M point, which shows actually this is in the superconducting state. So you clearly see the bending off, you know, the Bugov type of quasi-particle type structure. So you see a superconducting gap there, and you see this this white stuff with the blue dashed line in there. That is basically the a replica band that shows exactly the same kind of structure. Even the bending off is the same. And you even see the second replica a little bit. And that looks like an electron phonon coupling thing of some sort with phonons of the order of 100 millielectron volts, so 90 millielectron volts to 100 millielectron volts. Okay. And just going on quickly, this shows that again, and we see here, I've now drawn this blue line at the bottom of the superconducting M point, at the M point, and of the superconducting material, and you see that there is a clear gap between the bottom of that and the top of the whole band at what formerly was a whole band at the gamma point, oppositely dispersing. Okay. And that tells you that if this material, so this material has to be doped, because you cannot have, you know, a non-integer number of electrons just floating around without being compensated. It would have to be charged. It cannot be neutral, charge neutral, the whole material. Okay, so it has to be, so if we would take out those electrons, then this material in the rigid band-like sense would be a semiconductor and not a metal in the first place. So this material in the undoped phase, according to this, should be a metal. Now, I just want to talk about these replica bands, but I want to be very short because I want to get to the rest, which is more interesting. There's two ways of getting these replica bands. One way is that there is an electron phonon coupling of the d electrons, which are the electrons basically at the Fermi energy of iron, coupling with the phonons of strontium titanate. And it would have to couple with these Fuchs-Kluwer type phonons, and I'll describe them in a second. And that's those are at about 100 millielectron volts. They're the longitudinal optical phonons in the bulk that are actually the transverse optical phonon corresponding to that longitudinal optical phonon is your soft mode. It's at 10 millielectron volts or 15 millielectron volts. Okay, very important. But it could also be that the electron on its way out is actually exciting phonons. This is very common in photoemission results, where you can have plasmon satellites, for example, coming in as shake-off, people call them peaks, and they could be extrinsic or intrinsic, caused by either the fact that you have removed an electron from the iron and have a hole propagating there, or for the fact that the electron going out is actually exciting the phonons. And I just want to, so those are on the left-hand side here, that shows these two different types of things that could be happening. In photoemission, you have an electron coming out. Now, the reason why this is interesting is because there are high-resolution electron energy loss experiments done where you shoot an electron in on the same system, electron in, and scatter it more or less specularly and look at what the energy loss is. And that energy loss spectrum is shown on the right-hand side under the H reals, okay? And you see that those peaks in the, so this is the zero loss line here. And the peaks that you have, there are low energy phonons, of course, but then you have a peak here at about 60 electron volts. And actually you can see this replica band here also. It's at about 60 milli-electron volts. Okay, and it lines up with this peak here. I think I show that here. Oh, I first went over to this one. So this peak here, this real big replica, lines up with this one here. And that one lines up with that one there. And they look very much like the spectrum that you get for electron energy loss spectroscopy. Okay, so the question then is, here's now a second order peak, which also was there actually in the electron energy loss. So how do you, so you can, the electron energy loss stuff is very well understood. It's from way back when in the 1970s, Fuchs-Kluwer and so on, they did this work on surface phonons, which basically in this case are the longitudinal optical phonons of the bulk, which are shifted a bit at the surface. Okay, and you can get everything just from the infrared data. Just we have no adjustable parameters. Everything comes from the infrared data, where we have all of the phonon frequencies. And I'm going to talk specifically about this one. Here is the phonon frequency at 400 Kelvin. It's very highly dependent on temperature. This is a transverse optical phonon at 14 milli-electron volts, and it has quite a large width, and it has a huge Q. The Q basically is the static dielectric constant. Okay, that is the oscillator strength, the amplitude of the oscillation. If you go down to 15 Kelvin, that energy goes down to 1.4, it's overdamped, and the Q goes up to 20,000. However, there is no temperature dependence actually seen in these photoemission or in the intensity or in the electron energy loss spectrum. And that's because there's a rule that omega squared times Q is a constant. Okay, so we get rid of that first, okay? So this is the transverse optical phonon, and you know from the Lydane, Sachs, Teller relationship that the longitudinal optical phonon is the transverse one times the square root of epsilon naught divided by epsilon infinity. And the Fuchs-Kluwer surface phonon frequency is just the same thing, except you add a 1 because it's a surface effect. The vacuum has a dielectric constant of 1, epsilon naught plus 1, and epsilon infinity plus 1. And you can work out this theory perfectly, and you get beautifully all of these phonons, transverse phonons, yield you a Fuchs-Kluwer phonon that you see in electron energy loss spectroscopy. And this is a Q equals 0. It's a longitudinal optical phonon that is perpendicular to the surface, polarized perpendicular to the surface. So if I just look at a material and have an electron coming in at fairly high speed, coming in like this, then as it crosses its electric field, of course, in the perpendicular direction would be pointing in that direction, but there's a horizontal field, but it is oscillating, it is pointing, it is pulling that atom to the left here, and when it passes it, it'll pull it to the right. And that, because it's going fast, it averages out because the atom doesn't have time to move that quickly, okay? That's seen here. The arrows change, right? There. If you now go to the end, way out here, all you have left then is that you've left behind a time-dependent perpendicular field, right? And that time-dependent perpendicular field is the one that excites that phonon. And that phonon, if you do a Fourier transform of that, it has that frequency component in it, and it will excite that phonon. It has a very strong coupling to it. Okay. So is it extrinsic or intrinsic? So many people have tried. There's been theory done, a very beautiful work done by Lee and on this. And a recent paper, for example, they had also with Tom Devereaux, they had this picture of having an oscillating dipoles like this, and they did a quantum Monte Carlo type calculation, oscillating dipoles polarized in the Z direction here, in the vertical direction, and they calculated what a d electron in iron selenide by modeling it with a tight binding like model, what the d electron in iron selenide, how it would couple as it moves through the iron selenide. Now, obviously, well, pretty obviously, it doesn't couple actually for this Q equals 0 mode. The Q parallel is 0, but it starts coupling for a Q parallel in these oscillators, a Q parallel, which is finite, okay? However, you got to be careful with that. Oh, shoot, now I'm here. You have to be careful with that because the if you have a Q parallel, then this is not a longitudinal optical phonon anymore. It's a transverse optical phonon. And the energy of the bulk transverse optical phonon is at 15 or 10 millielectron volts. So in fact, although the transverse optical mode has a much lower energy, it has a gigantic Q, so it could couple very strongly. However, the in TC, oh shoot. However, in TC, here we are, in TC, that phonon frequency is the prefactor. And so I can't imagine that it could give you anything more than perhaps a 5 degree Kelvin change. We actually did what I call a poor man's electron phonon coupling calculation, just to see what happens if we move the oxygen atoms in this polar mode in the strontium titanate and look at what happens to the iron selenide band structure. And remember, the iron is about 4 angstroms away from the surface of STO. Okay, so so we then did 2 things. These are Elias calculations. We just moved the oxygens up and down relative to the titanium. And another way is to stagger then the up-down mode. I show here the up-down mode because that's the one that is expected to couple most. That, of course, is the transverse optical phonon, and because it's at the zone boundary, okay, with a large Q. And then you just look at the band structure, and you see absolutely nothing happening. So the iron d electrons really seem to be insensitive to what is happening so far away in the strontium titanate. Now, there is in our paper that we published about this, about the extrinsic energy loss, we also gave the smoking gun experiment as to how to determine what it was. And that's the photon energy dependence of the replica intensity. It should go like this if it's extrinsic. And many people have tried to measure this. It's very hard to do simply because of the very large background. If you look at this spectrum here on the right at the bottom, you have this very huge background here, and you don't know what the shape of it is inside here. So it's very difficult to say what the relative intensities of these peaks are. But there's a very recent experiment, and as I say, there's a lot of experiments, and they go all, I know ZX is a group, and Stanford and in Berkeley, they've tried very hard also. We have also, but we simply couldn't make much sense of it. But here's a paper that just recently came out by with Daryl Shalom, and so these are good people, and Kyle Shen and so on. These are very reliable results and very nice experimental results indeed. But again, you have this large background that these things are sitting on. And what they did is they used a kind of a spline method. So they just pinned the points in between the two peaks, the blue one and the red shaded one, pinned the background there and pinned it on the other side over here and a few other places, and did that all the way through, okay? Now, the problem with that is that there is another peak in between here. Yeah, there is another peak. That's a 60 millivolt peak. And if you change that spline background in that region, just a little bit, in this region, just a little bit, then the intensity of this one will immediately increase by a lot. This spline always has to be a bit lower than what the experimental data shows because of the overlapping tails of these states that you have, okay? So it really isn't correct to do this. However, they did it, and what they found then, if they do it this way, is that it's constant. And that's exactly what you would have expected for electron-phonon coupling, intrinsic electron-phonon coupling. Okay, so they, let's just assume this is correct. I don't think it is, but we'll see. But what they then find is that that intensity ratio between these two, between the satellite and the main peak, that of course tells you something about the electron-phonon coupling, lambda. And if you put that, if you use that electron-phonon coupling to enhance the TC that already was there because of the electron doping, which is about 40 degrees Kelvin. So just from electron doping, the temperature goes up to 40 Kelvin. And and you would get about a 15% increase, okay? So it would go to 46 or something like that, which means that it's very small. So I say that, well, okay, I don't really want to worry about this terribly much anymore, simply because it seems to be such a small effect that it really couldn't, even if it was there, it couldn't really affect the superconducting transition temperature much. So we're left with the problem from why. What's that due to, this large increase in the superconducting transition temperature? And then we come into a very big problem. An iron selenide monolayer on strontium titanate, as I just showed you, should be a semiconductor, okay, with a small gap. And the bands at gamma are all below the Fermi surface in the experiment, and at the M point are above the Fermi energy at the M point. And what you get in density functional theory is that those are degenerate. In fact, density functional theory has a big problem with all of these, okay? So this is done with iron selenide on strontium titanate, and then separated with the assumed lattice constant of strontium titanate. Okay, so what do we need to do to get an indirect gap in the undoped iron selenide? Well, it's a very difficult problem, actually. You can do all kinds of things, and it's very difficult to get a gap unless you go to magnetism. And we know from the work of Ole Krogh-Andersen that, that whether you have a magnetic moment on iron or not very strongly influences the selenium to iron plane distance, okay? The distance that you generally get from density functional theory is much smaller than it is experimentally. But as soon as you put in magnetism, then that distance becomes much closer to the experimental distance that is measured. Okay, so magnetism is something that that has a very strong coupling to the lattice, and this sort of matches with what we just heard from Bard about the 1111 material and other iron nictide-like systems. Okay, so let's go and have a look at this. So this shows you the density functional calculation just in an Lsda calculation. And it's relaxed. And if you do Lsda, you actually find, and this is G-type This is not stripy. This is G-type. Now, for many of these things, as far as lattice constants versus magnetism is concerned, the magnetic order really doesn't matter so much. What matters is whether or not you have a local moment. And the reason is that if you have a local moment, you cannot have 2 electrons in every K state. This means that these anti-bonding iron D states, relative to the selenium, these anti-bonding iron D states, you have to occupy more and more anti-bonding, higher energy anti-bonding states. And as soon as you occupy higher energy anti-bonding states, right, then the distance will be, the bond itself is becoming weaker and the distances are going to become larger. And this is exactly what happens. We've done this study for the iron oxides, for iron halides, and every time, if you look at a low spin, high spin transition, you get the same kind of thing again. In, for example, lanthanum cobaltate, okay? So this, whether you have a local momentum, right, matters much more than whether or not, or how it is actually ordered. And that's what I want to show you. So this looks very, very strange. So this band structure is completely different now. There is still between, there still is a hole pocket and an electron pocket, although at 0, it seems at the M point, it seems that the electron pocket has disappeared and you only have a hole pocket, okay? And you have this strange band, which is almost flat, crossing very close to the Fermi energy. And the magnetic moment is distributed all over the place. It's 1.7 Bohr magnetons. That's what you get if you look at the minimum distance or the minimized density functional distance of 3.7 angstroms for the lattice constant, 2 atoms per unit cell, 2 irons. Okay, and by the way, the iron selenide, the iron selenium, the distance of the selenium to the iron plane now is 1.45 angstroms, whereas in the non-magnetic case, it was 1.37. So this shows you exactly this effect of the elongation of that bond simply because you're occupying antibonding orbitals. And if you switch on a small u, 1 eV, it changes completely again. And if you switch on a u of 1.5 eV, it changes again completely and you have a huge gap. You have a gap. Remember, your Fermi energy here is always put at the top of the valence band, okay? So in DFT, that's the usual way of doing it. So the gap here is almost 1 electron volt. Okay. And you have this very flat band right at the Fermi level. And it has a very strong Z squared character, not XY, not Y, X, Z, Y, Z, but Z squared. Again, the lattice constant now is very large. It's 4 angstroms. And when you stretch things out horizontally, the vertical distance will decrease also, okay? So the non-magnetic, if you had this kind of lattice constant, the selenium would be much closer to the iron plane in the non-magnetic material. But actually, the distance now is 1.42 angstroms, which is much larger than, for example, if you use a Poisson-like ratio to determine what that distance is, it would be more like 1.30 or 1.28 angstroms. Okay, so again, magnetism, larger magnetic moment gives you this very huge change in the selenium to iron plane distance. Okay, but this is very strange, and we don't, this need not be the right answer, by the way, that this is the right electronic structure of this material with this DZ squared band here. There's many other examples where we know that if you have these kinds of magnetic moments, then things like multiplet theory becomes very important. And multiplet theory is something that you can't do in density functional theory. Okay, so it is a purely atomic thing. And multiplets could cross each other, as they do in the cuprates. They could cross each other relative to what you would get from a density functional calculation, simply because they are multi-Slater determinant states and not single Slater determinant states. Okay, so, but something like this is going to happen. But what that band, those bands exactly are, that we're not sure of actually. Okay, so we then were looking at also other things that might happen. For example, the top layer, the top selenium in this STEM data down at the bottom, but also from the very beautiful surface truncation rod experiments that Kazhu did, actually, that those they showed that the selenium actually is not symmetric. The iron is not symmetric between the two selenium layers. The layer at the bottom is a little bit closer to the iron than the layer at the top, the selenium at the top. Okay, so we tried that, but that doesn't really do much to the band structure actually, although it has a very interesting effect. It has the effect of, if you do the density functional and Lsda calculation, you then find that you, in this G-type, you find G-type antiferromagnetic order, so not stripy. That doesn't mean that it's not stripy, but the lowest energy is not stripy in this calculation. But you find that the two moments up and down are not equal. So now you have time reversal symmetry breaking. So be careful. You have now a dipole and time reversal symmetry breaking. I wonder if that really happens, but we don't really know. I'm going to skip this part because I'm running way out of time. I do want to mention this. So if the material is doped, then of course, you have taken electrons from STO because the STO had extra electrons in it at the bottom of the D band. Okay, so they're over here. The Fermi energy for STO would be up over here, and there is electrons in the conduction band, the iron D band of STO because of the niobium doping or oxygen vacancies. And those are actually, the work function there is actually lower than the work function in iron selenide. And that means, and that I show on the left-hand side here, that means that those electrons will flow as much as possible to the iron selenide. This means you get a dipole layer shown at the bottom here, the plus and the minus signs. Okay, so the STO is going to be positively charged, probably accumulated at the surface, and the iron selenide will have a negative charge. And when you do that, you have a kind of capacitor. They, of course, attract each other. And indeed, in density functional theory, you find that now the distance between the iron selenide and the STO gets smaller. But there will be an equilibrium where that all, where the amount of charge transfer simply is stabilized. And that turns out to be this magic number of 0.12, I think it is, per iron. Okay, I am going to skip most of this. I want to now talk about spin fluctuations. And I want to stress that there are two kinds of spin fluctuations. Is it the 0-point spin fluctuations, as you have in an ordinary antiferromagnet, as in perhaps the cuprates? So if you have a spin 1/2 system in 2 dimensions, antiferromagnetically coupled, then the nearest neighbor spin-spin correlation function is minus 0.33, right? But in Ising, if you didn't have the quantum fluctuations, in Ising, it would be minus 1/4, minus 0.25, okay? That is the kind of spin fluctuation where one spin flips up and the other one spins down. That is the kind of spin fluctuations that we generally think are important for the magnons, right? They are the magnons. They give you the magnon propagation, and they're the ones that we think are important in the cuprates for superconductivity. Whether that's true or not is also still up in the air. Or is it a quantum fluctuation of the magnitude of the local spin? Now that sounds a bit strange, but let me just show you what I mean. So if we have, we have here, we have an XZ orbital and a YZ orbital and a XY orbital on two neighboring irons. Shall we say the irons are in the X direction, okay, the neighbors. Then we have this kind of a picture. We start out with, and we put a magnetic moment on both of them, and we'll make them, put them antiferromagnetic, okay? And then look to see what happens. So I have the XZ, which is the black one, and the XY, which is the red one. And they both can hop to the neighbor, okay? So I hop, I then hop a neighboring spin here. I hop one of these spins to a neighboring XZ. No, that was the XY. Okay, this hops to the neighboring XY. By the way, an XY can't hop to an XZ, and an XZ can't hop to an XY. Okay, so the XY hops to the XY on the neighbor, and you get this picture up here, right? So now you have a spin of a half on each one of them. The energy cost is U plus J Hunt, putting the energy of this thing at 0. And the hopping integral is T. Then you can go ahead and you can hop this black electron from the XZ orbital to the left, giving it to the XZ on the left. Then you get this picture here. This is a spin 0 state. Okay, and this here costs you twice Hund's rule to do this. And you have many of these possibilities. Yeah, you can go this way, but you can also flip spins around, making singlets or triplets. And so you have many, many possibilities, meaning that you have a lot of degrees of freedom with degenerate energies of hopping. You can also hop, you can also have a spin on the YZ, hopping in the other direction, okay? Also with the XY orbital. So again, you have more possibilities of hopping back and forth. Plus all of the spin flip cases and equivalent paths and pairwise hopping in the perpendicular direction with YZ hopping. And if you see that the parameters are, you know, J is maybe about 2, maybe 1 or 2. Sorry, this should be U, I'm sorry. This should be U is about 1 or 2. The hopping integral is about 0.5 maybe. And the Hund's rule coupling, well, maybe it's 0.7, it could be 0.5. This is why Cotillard calls this a Hund's rule metal. It could be 0.7 or so. And you see that these, if you multiply this hopping integral here by the degeneracies that you have, right? Or by the square root of the degeneracies of what it can hop to, that's basically what you have to do. Then that easily multiplies this by at least a factor of 2 or 3, right? And then everything is of the same order of magnitude. So everything is mixed together very, very strongly, okay? And then you have basically a reduced magnetic moment on each atom. And the reduction of that magnetic moment is going to be extremely sensitive to the parameters. So that is the electron phonon coupling or electron lattice coupling that is all horribly sensitive to interatomic distances and to orbital ordering, of course. And this could even result in orbital ordering, but of a complicated kind, yeah, of a orbital exchange type of process between atoms. I think this is something that Daniel had also mentioned, or maybe other people. So I think that these kind of things are really important fluctuations, also fluctuations which actually also can lead to pairing, okay? I think that's Kaliulin was one who described pairing in these kinds of fluctuations. Okay, conclusions. Well, I don't know. There are none, actually, except that I think that everything is important. And certainly magnetic lattice couplings are extremely important. I think these magnitude of the magnetic moment fluctuations are also extremely important. And maybe that's why we have these very strong dependencies on strain, on whatnot, when also in the band structure calculations. Thank you.
Very nice. Thank you, George. So before we have a question, so let me quickly announce, Chimio asked me to announce that next week we'll have a JP Pagoroni, also Peter Avenatti from Illinois. JP is from Maryland to give talk, so please attend. Yeah, okay, so first question, Bernd.
So I just want to comment on that because I like this picture very much, because it's not only orbital ordering, which you can explain this way, it's also the sensitivity to the external pressure.
Yes.
That's something which is, let's say, iron selenium. Take iron selenium, you can, just applying pressure, you can go from whatever 8 Kelvin to 40 Kelvin. You can play the phase diagram with external pressure, and that's all very, very difficult. It's very much different from the cuprates. And I think this scenario where these high spin, low spin things plays a role is a natural way to explain that. And I like it very much. And then the other thing, the strains comes on top of that, orbital ordering comes on top of that. But that's, let's say, also a very interesting thing. Yeah.
Well, this could also result in orbital ordering, actually, in principle.
Yeah, of course. But this is a different channel. The other channel,
yes.
Even the easy one, the hydrostatic pressure should be large in this scenario, and that's the pressure dependence, and that's actually what has been seen. I think it's also
well, that's what I found so interesting about your talk also, was this very, very large strain dependence that you have. Yeah.
Okay, more question?
Yeah, hey, George.
Hi.
This picture which you show now here with all this fluctuation, can it be really directly related to all this pneumatic stuff?
I think it can be, actually. I haven't worked through.
Did you try to do it, actually?
I haven't yet tried to do it. As a matter of fact, I wrote this picture this morning, but I had it in my mind already for a very long time. But this is the first time that I've actually shown it. It's not published or anything. But I really feel that because of these degeneracies, right, you're going to have a Jan-Teller problem. And I think that because of that, you're going to, it will want to do something. And it could, the one thing it could do is indeed orbitally order and give you the pneumatic type of phase. Also, as far as the lattice is concerned. And it could even do that before it does the magnetism, right? Because it's so strongly coupled to the lattice.
And this picture,
by the way, this would be an electron-phonon coupling, where the phonons, where the coupling is in the Hopfing integral, not in the on-site energy.
Yeah, would it depend on the material, whether you are dealing with iron selenide or 122 or 1111, or it would be more or less the same in the whole class of this?
I think these things in themselves, well, these parameters, as I said, things are so sensitive to what these parameters are that I can imagine changes, but the qualitative physics, I think, would be the same. I think this would happen all over, but by changing parameters, you can either go into the pneumatic phases, or you could go into a magnetically ordered phase, or you could spin density wave phase, right? And maybe even a superconducting phase.
If I can only ask a very short question, experimental question, essentially. You say that superconductivity itself in iron selenide and STO is due to electron doping. But for that, you really need this STO, which is already kind of either oxygen depleted or with neodymium or so on. So experimentally, does it really depend on the quality of STO? Because if you have very stoichiometric, very good STO, then you wouldn't get any superconductivity at all. Is it really what people
nobody actually knows because all of the STO materials. So the STO that is used, and that was this double layer I was talking about. STO, when you what they do in order to get rid of the oxygen vacancies as much as possible is they heat it up to around 900 degrees Kelvin and in oxygen. And that removes the oxygen vacancies. But what it also does is it removes some strontium from the first layer. And you then get an STO, which is basically almost pure, with a double layer of a double TiO2 layer. But it doesn't have the same structure as the terminating layer of STO, the TiO2 layer. It has a complicated structure. These are these beautiful results of this surface truncation rod experiments by Clejou and who was it? Anyway, you can look them up. I think it's reliable that and everybody really assumes now, and also the STEM data also shows you this double layer of STO. In other words, the subsurface strontium oxide layer is removed.
But if it's very difficult to make really stoichiometric STO,
yes, almost impossible.
Maybe one can experimentally do just the other way around, just to try to deliberately dope it by niobium and see whether
we are exactly
more favorable for superconductivity.
That's exactly the experiments that are being carried out right now at UBC, and those are experiments. You can do that in several different ways. But you're perfectly right. That's why, and there's a very interesting, I just saw it just this morning, paper in the archive about iron, monolayer of iron selenide on top of graphene. I think it's a double or a triple layer graphene, which is on top of silicon carbide. And there, they claim, and they haven't done any photo emission. These are only small little islands of material, but they have done what's it called? The interference scattering and scanning tunneling microscopy, okay? And from that, they could infer what the band structure really is. And they claim in that paper that actually that has a hole pocket and an electron pocket, but the height of the pocket is only a few millivolts. So you have basically 0 electrons, but you also have a gap, which is a superconducting gap, they claim, which actually is comparable to the Fermi energy in that particular case, meaning, we're perhaps in trouble with BCS theory. But I don't know how reliable that is, especially the analysis of these scattering experiments, these backscattering experiments in the scanning tunneling experiment, how well you can actually predict the electronic structure to this kind of an accuracy, I think is very difficult.
Okay, thanks.
Okay, so the last question by Qimiao.
George, nice talk. So I just want to follow up on this picture that you're showing on the screen. There's some interesting systematics in the total spin spectral weight that's measured in the pnictides versus in the selenides. And I was wondering whether you have some thoughts.
You mean in the neutron scattering, or? In
the neutron scattering, integrate over Q, integrate over omega. You get something like somewhere around 3 or 4 Bohr magneton square per ion in the arsenides, and you get much more than that in the various selenides.
Yeah, well, I showed you pictures in LDA plus U with LSTA, where you actually have 3 Bohr magneton magnetic moments. Depending, but then the lattice is also very stretched. it would automatically want to stretch, and the selenium would want to come down into the iron plane almost. Yeah, you'd almost get a rock salt like like structure in the end. But these moments we feel are really quite large. So what we get is something close to 2 Bohr magnetons, which means a spin of 1, right?
No, but the question, I think, to me, it's interesting to at least look at the austenites and ask question, what is reducing the integrated spectral weight? Of course, neutron doesn't see it, doesn't necessarily mean it's not there. So
that's right. No, that's right. It's difficult to say because you know, the form factors here are going to be very, very difficult, right? These are really complicated form factors in neutron scattering. So I really don't know how that would work out. Actually, with a model like this, we might be able to even look at what the form factor would do. That's actually rather an interesting question. Yeah.
Okay, so with that, I mean, let's thank George again. Thank you so much, George.
Thank you.
For giving a very nice talk.
Yeah.
Yeah.
See ya.
Thanks to Ben as well.
Yeah, thank you. Yeah, thank you, everyone.
Hi, before this ends, I just wanted to say hello to George.
Hey, Jim, how are you doing?
Hey, Jim Allen.
Really fun to listen to a talk from you again. So in these weird times, it's just a nice chance to do that. It's good to see you.
Well, good to see you, Jim. Everything okay?
Yeah, we're doing fine. So
great.
Greetings to you and Marge from Kathy and me.
Okay, thank you.
All right.
Sure. Yeah.
Thank you.
Stay safe.
Yeah.